I was there, but after that, I have not been around.
Fine, ma'am. That is too good that you are here with us. And right now, I can see 49 participants have already joined. And I can see in daily sessions, approx 120 participants are there at any point of time. So Dr. Sumit was there in the morning and he briefed about what are knowledge graphs, how to design and how to use them. So I hope the participants will enjoy. I think you're ready with your presentation and you have, will you like to put the title slide?
Could you please repeat?
Will you like to do the slideshow? Will you like
Yeah,
to present?
I'm ready. Yes, absolutely. Yeah.
So you just put the title slide and I like to introduce you to my participants for the time being.
Sure.
Dr. Maya Rmanath is an associate professor in the Department of Computer Science and Engineering at IIT Delhi. She completed her PhD from Indian Institute of Science and was a researcher at the Max Planck Institute of Informatics, Germany, before joining IIT Delhi. Her interests are in the area of data management, including database systems and information retrieval. Thank you, ma'am. Thanks for being with us. Over to you. You can kindly start your talk.
Okay. Thanks, Sarika. So, welcome to everybody for this post-lunch session. I hope it was not a very heavy lunch that you feel sleepy. um, the talk is going to contain quite a few details. In one way, it is both good and bad. I think it is good because even if you doze off a little bit, you're not going to miss a lot because those details can always be, you can always look back on it and figure out what you have missed. So there is nothing very complicated about the details. And it's bad because it might actually put you to sleep, but I hope not. So first of all, I would like to thank Dr. Sarika Jain and her team for organizing this workshop. It's a very painstaking thing to do, trying to get people together, and there are a lot of administrative issues that need to be done. And she has been at it, I know, for many weeks now. So thanks, Sarika, for giving me this opportunity to come and present. And even before I start with the technical part, I have to make this obligatory statement about how we are all meeting in COVID times and how we are all stuck at home and how strange it is to sort of give these talks and listen to these talks without being face to face with each other, right? Okay, so let me just go right ahead to the topic of today. So I'm sure in the morning, you have learned quite a bit about knowledge bases, construction techniques, and some terminology related to it. And knowledge based querying, I think Sumit was planning to cover entity search. I don't know how far he got in that. But I think you have a good idea of what knowledge bases are all about and some of the challenges in the construction of these knowledge bases. So, what I want to do today is to go into some very specific case studies based on my own experience in constructing these knowledge bases, and then give you some engineering details about how how practical it is, how difficult it can get, and so on. So let me start with this one slide introduction. Not sure if you guys need it, but there is a very specific point I want to make with this slide, right? So this is a knowledge base with subject, predicate, object, which are the three columns. And we have some general knowledge here, information about physicists, basically people, information about movies, and so on. And these are the general purpose knowledge bases that people usually talk about when they say knowledge bases like Yago or DBpedia and so on. So apart from that, I have a few triples from other kinds of domains, right? So here you can see some four triples from the domain of computer science specifically, right? So the subjects here are concepts in computer science like topological sorting, group testing, Iron, Python, and so on. And you have coding theory, Ethernet, and these kinds of entities, which are very specific to the computer science domain, are related to each other in certain ways. And that's what these relations are talking about here, right? So group testing is an application of coding theory. And then here in purple, I have more triples, which are different from both these general knowledge facts here and the concepts of computer science facts here. They are basically opinions, right? So there is a person or a stakeholder person, people like Barack Obama, Donald Trump, stakeholders, which are here basically countries like UK and Scotland. And there are some very controversial political topics at this end. And these triples simply sort of record who feels what about these highly political topics, right? So Barack Obama supports military action in Libya. Donald Trump opposes illegal immigration. UK supports Brexit, but Scotland opposes Brexit, and so on, right? So opinions, triples, different from the other kinds of triples that we saw here. And again, going to this part here in blue, these are again very domain specific. It's from the domain of biochemical engineering. And here we have entities on this side which consist of things like microbes. So Pseudomonas is a microbe. Hydrocarbon degradation is a chemical process. On this side, you could have microbes and processes again, but you also have things like substrates and locations and so on, right? And these facts are basically talking about the occurrence of a particular microbe in a particular kind of place, a certain kind of chemical process occurring on a particular microbe in a particular place, and so on, right? So if you ask me to sort of explain exactly what these are, I wouldn't know because I'm a computer scientist. But this is something that is going to be interesting to biochemical engineering people. And I will talk more about why that is the case later on in my talk, right? And finally, I just wanted to mention another specific kind of set of triples, which are basically events, right? So you could have triples such as Pulwama attack was targeted towards the CRPF Jawans and orchestrated by JEM and so on. So these are events that happened in the recent past, again, different from all the other kinds of triples that we have here. So the point I want to make with this slide is that extracting each of these triples is going to require slightly different kinds of techniques that we need to apply, right? Okay, so here is the, I just put up this blurb here because I wanted to sort of emphasize the place of knowledge bases in the grand AI dream, right? So AI, it's been there for many, many decades now, right? The ultimate goal is, of course, to sort of organize all the information in the world, which is readable by machines, which machines can reason about and help us make decisions on, and so on. And right now, because of the World Wide Web, we have all sorts of information available to us at the touch of a button. And we are, building more and more tools to organize this information into this self-maintaining encyclopedia of all human knowledge. So that's like the grand AI goal, to organize it and to use it, right? So, okay, so this is a knowledge base. And I said it has 3 columns: subject, predicate, object. Even though we can do a lot with this definition of a knowledge base, I have to say that this knowledge base is quite limited, right? So starting from some very simple things, things that could go wrong in a knowledge base, right? So The first thing is, are we sure that entities and relations have canonical names, right? So these knowledge bases, remember, we are extracting from the information we have, maybe on the web or digitized information online, and we are organizing it into this nice table. But one of the first things that we have to consider is it clean, in the sense that if you extracted information about Einstein from one source and Albert Einstein in the other source, are they probably the same person or not, right? You want your knowledge base to sort of say that Albert Einstein and Einstein are the same person. Of course, it depends on the fact that you have extracted, but very likely Albert Einstein is the famous physicist and he's often referred to as Einstein. So when they're referring to the same person, then you want one canonical form of the name Albert Einstein to exist in your knowledge base. And similarly for the relationships as well, we have discovered, invented, and developed three different relations that we might have extracted, but they're very close in meaning to one another. So whether or not we want to make this distinction is a design decision that we may have to do. And even tougher than this is to sort of say all these three things mean approximately the same. So I'm going to store it as under one canonical name of the relation. Okay, and this is quite challenging, and people still work on it in spite of lots of methods being available to do this. The second challenge, it sort of goes to the philosophy of these knowledge bases, right? So here I'm talking about the truth of the triples that you have extracted, right? And there are two facets to this truth. One is to just look at the extraction accuracy, right? So for example, in the first triple here, it says Spielberg directed Schindler, which is not quite right, because very likely in the source, which is probably a sentence from which this fact is extracted, you would have Spielberg directed Schindler's List. And Schindler's List, if that was here, then that would be accurate. But at the moment, it's not accurate at all. It's an incorrect extraction, and we have something that is not right in our knowledge base. But the more interesting question is, even if the extraction is right, is it true? Right? Because many of you may know that there are lots of conspiracy theories about Elvis Presley, right? So long after he died, people were saying, no, he's actually secretly alive, and he's living in hiding and so on. And I'm sure there are lots of articles that appeared speculating as to where he was and what he was doing and so on, right? And one such article might speculate that Elvis Presley lives on Mars, which sounds ridiculous to normal people like us, but extraction is correct, right? But the problem is that your source is pretty unreliable, right? So that is another issue that needs to be considered when we are doing general purpose, this knowledge graph extraction. Another issue is, there are two facts here. Manmohan Singh is a finance minister, Manmohan Singh is a prime minister, but they're valid only at specific time periods. So this sort of says that the binary relations that we have, right? So the subject, predicate, object that we have, is just not sufficient to express all the information that we want. So even though in this talk we are only going to deal with these three columns, subject, predicate, object, I think it's important to realize that we are very far from representing everything that we can in this precise manner, right? So another example here is that Einstein in 1921 won the Nobel Prize, right? This cannot be represented as just a single triple. It will require at least a four tuple or a nested triple to express. And of course, all the text that you have cannot be expressed as triples, right? And we will see an example of this towards the very end of my talk. But I think this is intuitively quite obvious that we cannot do this. And finally, something that I'm not going to sort of touch on at all in this talk is to evaluate the knowledge base that has been extracted. So typically we use the two metrics, precision and recall, right? So precision talking about how many of our triples are correct, how many triples that we extracted are correct. And recall basically says how many correct triples have we extracted. And in fact, evaluating the precision is sort of doable because we usually do it by sampling from our knowledge base and having users manually look at it and say whether it is correct or wrong. But to evaluate the recall is quite difficult, right? Because there is no such thing as a complete corpus. You likely will never see the entire corpus, and there is no way you can figure out, even in a large corpus, there is no way to figure out whether all possible correct triples have been extracted, right? So, in the absence of this, it's sort of our best guess. Um, Precision can be quantified to a certain extent, but recall cannot be quantified. So, what can we do with that, right? Um, so I just have this small thing here. Um, Besides just sticking with triples, we can always extend our KBs with additional columns and additional information. So starting with timestamps. So for example, you can have a timestamp for each of these tuples here, and provenance, saying where the triple actually came from, and location. So, for example, if you're looking at events, right? So, Pulwama attack targeted CRPF, but where did they do it and when did they do it? So, you probably need two more columns to correctly capture that event, right? Textual context, nested information, and a lot more can be done with these knowledge bases. Okay, so we know that knowledge bases, as we are dealing with them today in this talk, are quite limited, but there is still a lot of things that we can do about it. And obviously, once we organize all this information in this nice table, one of the first things we are going to want to do is to query it, right? So you don't want to just store the data, you also want to retrieve the data. So here I just thought I would list a few examples. Some of these we will be talking about in a little more detail later on, right? So here is an example. List the Nobel Prize winning theoretical physicists born in Germany. Um, Pretty confident that Google may not give you the result for this, even though the information is already out there, right? You probably have to do an aggregation step. So you can type in the query to Google, and it gives you a number of different web pages which lists these theoretical physicists who are born in Germany, who have won a Nobel Prize. But unless there is already a page which has made this list, Google will not be able to find it. But in contrast, we can easily find it if we have organized our information in this triple format, right? So just firing a query on this knowledge base would be sufficient. Same thing with this, which comedy films have won the Academy Award for Best Film? Again, it is just a question of matching the triples to the query, trying to find out, if you have stored the genre, then you can find all the comedy films in the knowledge base. And then if you have stored awards that films have won, then you only have to find out which movies have won the Academy Award, and then take an intersection of these two lists, and you have the answer right here, right? But this next question is a little more interesting. So this basically asks, what are some commonalities between L.K. Advani, Somnath Chatterjee, and Manmohan Singh, right? So in a way, it is maybe easy to answer that all three are men, or all three were in parliament, or all three are politicians, and so on. Um, but basically, this is a query that asks the system to discover interesting connections among these three people. And I listed this query here because it is different from the two queries above, which can be expressed as a query, right? So, these can be expressed as a query in Sparkle, whereas this query cannot. It's a little more general. And I will be talking about this. We call this keyword queries, and I'll be talking a little more about this later on in the talk. Other examples of, all I need to do is match the query with the triples here. Did both Barack Obama and Donald Trump support the Iraq War? You just need to look it up. What kind of chemical processes involving acetone occur in the sea? Same thing. You just look it up in your knowledge base, and you're good to go, right? So the querying the knowledge bases themselves is one sort of application that we can think of. But I also wanted to list a few other applications which involve the knowledge base only as a sort of tool, rather than in the querying part we just had the knowledge base, we had our query language, and that's all we required. But there are many other applications that you may want to do. So, for example, this computer science concepts that we have here, it was actually part of a larger project, and one of the applications that we wanted to implement to address with this particular knowledge base is that of academic search. So, academic search, here is an example of a query that I might want, right? So, how can I search for research articles discussing applications of autoencoders? Now, obviously, we just go to Semantic Scholar or Google Scholar and we fire the query autoencoder, right? So autoencoder in the search field, and we get a bunch of results. And these results are quite good, and you can sort them in some ways. You can restrict the years in which they were published. You can do all that. So it's pretty good. But now suppose I want something more than just autoencoders. I'm interested in a very specific aspect of autoencoders. So for example, I may want to learn about algorithms for autoencoder training, for example, right? Or I might be interested very specifically in applications of autoencoders, right? So it's not just autoencoders in general that I'm interested in, but a specific aspect of it. So one way to do that is to add some extra query terms, right? Autoencoder algorithm, and fire the query again. But if you notice, the results that I get here are not really different from the results that I have in this list here, right? So just adding a new term, sort of trying to hint to the search engine that you're looking for algorithms to do with autoencoders, it's not quite working. So the problem that we wanted to address was, given a concept like autoencoder, and given a facet of that query that we were interested in, can I come up with a ranking model which would give me the exact good results for it? So here are some results from our system, right? So in this column you have a list of concepts. So autoencoder is what I started with. And here we have some facets or aspects that we are interested in, right? So applications of autoencoders, the top result that we got is exploring autoencoders for unsupervised feature selection, which is very clear in an application of autoencoders. For the algorithm aspect, we have here training stacked denoising autoencoders for representation learning. So this is specifically looking at algorithms to train a particular kind of autoencoder. Similarly, for implementation, the top result we got was parallelizing the sparse autoencoder, right? So what does this have to do with our knowledge base, right? So the way we used knowledge base in this application is to find terms for query expansion. So, in the knowledge base, we might have direct knowledge or relationships that directly say, something or the other, XYZ is an application of autoencoders, right? So XYZ is a term that could be interesting in expanding the query, right? So that's a very simple way in which we can use these knowledge bases for query expansion. There are also other ways, other uses we found for KBs to do this query expansion. But the point I wanted to make here is that constructing these knowledge bases, especially for very specific topics like computer science, enables you to implement certain kinds of applications which are not possible with a general purpose knowledge base. And here I just listed a few more applications, right, where the knowledge base is just a component in the entire application. So again, having to do with the computer science knowledge base, one of the things we wanted to address is answer questions like what are the prerequisites for learning about HMMs. So here HMMs, to learn about HMMs, maybe we need to start with what probability is, what conditional probability is, and there is a path that students can follow if they don't know about HMMs. These are all the concepts that they need to learn until they come to HMMs. And again, you can have a student interested in different aspects of HMMs, right? So maybe this person is interested in HMM applications or theory on HMMs and so on. So how can we come up with a tree of prerequisites that can help help guide the student in learning about HMMs? So that was one application that we did. And another application was a reasoning application, and it had directly to do with this biochemical database or biochemical knowledge base that we had, where we wanted to answer questions like which microbes are anaerobic, right? So, of course, one might think, just looking at the question, that isn't this just a matter of sort of matching something in the knowledge base, right? So there might be triples in the knowledge base which say microbe X is anaerobic. So if that triple is already there, then you directly have an answer to this question. But usually that is not what happens. What you usually have is bits and pieces of information like this, right? That some microbe is found in some particular environment, and certain kinds of um, processes happen in the same environment, and these processes could produce certain kinds of chemicals on which this particular microbe acts and so on. So these bits and pieces are what you're able to extract from the text, and then you need to put this stuff together in a reasoning framework, right, which an expert could provide. An expert could say, if all these things hold, then you can conclude that these microbes are anaerobic, right? So reasoning is one of the applications in which a knowledge base is a part of it. Okay, so let me now move on to um, domain specific knowledge base construction, right? So I want to construct knowledge bases of this kind. How do I go about it? uh, you will see that based on the application that you have, you might choose some very specific techniques. But before we do that, I want to talk about some general principles for domain-specific KB construction, right? So one of the things that was very, that's a real lesson for us to learn is that the source identification is extremely important. So you need to know exactly where you're going to do your extractions from, right? It could be, and here I sort of divided it into two kinds of sources: structured sources and unstructured sources. And of course, among the most popular structured sources is Wikipedia, because it's an encyclopedia which has information about everything. But Wikipedia is not the only thing. I mean, if you wanted movies, you could go to sites like IMDb. And for the computer science concepts, we actually went to a domain specific website called Webopedia, right? So all these websites, they have their pages organized in a very specific structured manner, right? So structured sources. And then quite a lot of information you might be getting only from unstructured sources. So for example, the biochemical knowledge base, we had to extract from research articles, right? So the articles that you choose, and if you wanted to do opinions, you would have to choose newspaper articles, right? So there is unlikely to be a structured source which gives you everything that you want. So newspaper articles, blogs, forums, reviews, all these are unstructured sources. And depending on how clean these sources are, how nice the English is, right? The English language, it has to be written in a nice way, because one of the tools you're going to use is our parsers. So parsers work well when the English is good, right? So you would want to choose these unstructured sources from from good places, good newspapers, right? So source identification is often quite key to extracting a knowledge base which is very which has high precision. And the next thing we usually do is to extract the entities. Again, this could make a big difference in the final quality of your knowledge base, because having a dictionary of entities can help you a lot in the next step, which is the extracting the relations, right? Having a really good set of entities, you can always concentrate on those sources or snippets where these entities exist, and stop wasting time on sources which do not contain these entities at all. So entities themselves can be extracted from structured or unstructured sources, right? So usually structured sources, it's a lot of engineering that you need to do. So for example, if Wikipedia was your structured source, and you just wanted the list of all people, the entities that you were interested in was the list of all people, then you would probably go to a bunch of pages in Wikipedia and take out the title of Wikipedia, right? Because everybody knows that the title, Wikipedia titles are always entities. And to extract the title out there, what you need to do is to write a wrapper. It's quite straightforward, even though the amount of work you will need to do, but it's quite straightforward to build such a to program such a wrapper. Um, and extraction from unstructured sources is a lot more tricky, right? Because again, extraction from unstructured sources, you would need to use parsers and part of speech tagging and heuristics, lots of these. And I will show you examples of lots of times that they just don't work. Extracting from unstructured sources is probably the toughest that you can do. And additional information on the type of entities that you're extracting might help you a lot. So if you know that I want only computer science concepts, it gives you some information about what kind of pages to look for and so on. And of course, entities themselves need to be cleaned up. And I won't be talking a lot about this, but this is a problem that people have been working on for a long time, and it's not like it is completely solved. So the examples that I gave, Einstein and Albert Einstein, are they the same person or are they different persons, right? So you want to reconcile two different ways of representing the same entity and representing the same relationship. Again, so for relations, we go with the same thing. So this part here will give you a huge dictionary of entities, right? So now you know the entities, you could start extracting relationships between these entities. Again, relations from both structured and unstructured sources. And here I make a distinction between relations that you know of, like ahead of time, you have decided that these are the relations that I want to extract, and relations that you don't know of at the moment. Okay, I thought there was some disturbance. Did someone have a question?
In the chat box, I can't see any. If any participant has, please unmute your mic and ask.
I actually can't see any participant because my screen is just full of the the slide, because I'm in presentation mode. But if someone wants to ask questions, they can sort of interrupt right now, or we can have a question answer session at the end for like say 10-15 minutes.
Yeah, we can do both ways. They can also unmute in middle. Otherwise, at the end, we can definitely have it.
Okay, so let me just move on for now then, if no one has any questions, right? Okay, so these relations, again, we can extract from structured and unstructured sources, and I make this distinction about the relations that you know ahead of time that you want to extract, and relations that you don't know at the moment, right? It might really depend on the text that you have, that you extract it. Uh, I will tell you what I mean in more detail. Just in, I think in the next slide, I will tell you about it. And of course, the same kind of cleanup as we did for entities, which is to reconcile the relationship names, make sure that they're in a canonical form, and so on. And finally, of course, you are not going to extract your entities and relationships once and then stop there. You also probably want to do some refinement of this, right? Um, since I'm just going to leave this part as is and talk about it later on, because many of the things that I need to talk about, I don't have a refinement step at all, right? But refinement again, this refers to sort of iterating over the knowledge base that you have, and you have extracted some information from there, and then you pass it again back to your programs, and you improve the quality of the knowledge base in that way. I know that is, that's a very vague way of saying this, but let me come back to it later on for this refinement step. So here is a sort of guide to how to use these general principles to construct each of those different kinds of knowledge bases, right? So first is the opinion base, where the sources that we decided on were newspaper articles. In fact, there were some 5 or 6 newspapers that we chose. Wikipedia, of course, and something called Debatepedia. Again, Debatepedia specifically because it was an opinion base, right? Um, and to extract entities, we made use of Yago. So Yago is basically derived from Wikipedia, right? And we knew what kind of entities we wanted. Things like countries and institutions and people. That was one kind of entity that we wanted, and we could derive them from here. But the topics, that's not so easy to know. So this, so to extract topics, we don't know what kind of topics they are, so we have to wait until we actually look at the sources that we have. And for relation extraction, it was very simple because we know exactly the two relations that we want. So this is not always the case. You don't always know what relations you want, and it may not always be limited to two relations. But in the case of this opinion base, we knew exactly the relations that we wanted: support and oppose. And all our sources were unstructured sources, which means we extracted everything from newspapers. So refinement, I'm just going to skip over it for now, right? Um, so I made this nice table. Maybe later, if we are sharing these slides, you could look at it. So since the first thing I'm going to talk about is the opinion base, let me get right to that, right? So far, sort of introduced what knowledge bases are and their applications. I'm sure I didn't need to convince you a lot about why we need these domain-specific knowledge bases. So let's go right into the first part, which is building an opinion base, right? So that is the first. One thing I want you to note here is that there was a specific goal that we started with. And the goal was map out the landscape of political opinions on controversial topics. So this seems like a very vague goal, and indeed it was, right? Because all we conceived of at that time was to simply extract triples of a person, support or oppose topic, and we wanted to extract as many of them as possible, right? Um, and we had, uh, newspaper clips like this. I hope this is somewhat visible. It's not a very sharp picture. Um, the fact is that politicians have a lot of opinions that they keep expressing all the time, right? Um, and they keep changing their mind as well. So it would be great, we thought, if we can organize this landscape of opinions, right? So it would be good to know which person said what about which topic. And there are a lot of controversial issues, lots of stakeholders, and actually many shades of opinions as well. Even though in this work we only considered support or oppose, so it was always binary, right? And here are some examples of the kinds of relations that we extracted, right? So Dalai Lama, I don't know if you guys remember Anna Hazare's anti-corruption movement. It was a while back, right? Um, so, well, now you know, right? Because that information is there in the opinion base. So, one thing I just wanted to point out is that it is still three columns, but instead of calling them subject, predicate, and object, I'm only calling them entity, polarity. So, polarity is simply support or oppose, and the topic, right? And I added this additional column just for understanding, right? So what was the context for extracting this particular um, triple? So if the sentence was supporting Anna Hazare's anti-graft movement, Tibetan spiritual leader Dalai Lama said or did something here. And from this, we extract this particular triple. Dalai Lama supports Anna's anti-corruption movement. And you will notice that Anna's anti-corruption movement is canonicalized here, right? Even though here it says Anna Hazare's anti-graft movement, that has been, that part, that topic has been canonicalized in this way here, right? So BJP supports it. Lalu Yadav had opposed it, and Anna Hazare himself had opposed FDI in retail and so on. So more examples like that, but in an international context, right? So this was the about the military action in Libya during Gaddafi's time, right? So Barack Obama, Nicolas Sarkozy, UN Security Council, they all supported certain kinds of military actions on Libya, while Germany, opposed the no-fly zone on Libya. And again, all of these triples have a context from here, probably extracted from newspaper articles which are international in nature, right? And finally, we wanted to organize the opinions we had into a network, right? So here you have various kinds of entities like the UN Security Council, Angela Merkel, and Anna Hazare, and so on. And here are a bunch of topics about which these stakeholders have an opinion. So FDI in retail, no-fly zone, Gaddafi's response to the civil war, right? And this O and S here simply indicate support or oppose, right? And once we have these facets or topics here, we wanted to organize them in a topic hierarchy, right? So Gaddafi's response to civil war was regarded as, war crimes in Libya because it was that brutal. And war crimes in Libya was just a part of the Libyan civil war of 2011. And Libyan civil war of 2011 was a part of the illegal immigration problem. So why was it this way? Simply because once the Libyan war started, there were lots of refugees pouring into the neighboring countries. And that was a big problem, right? So the goal was to come up with a whole bunch of support oppose facts of this kind, triples of this kind, and to organize these topics into a topic hierarchy. And we did it in these 4 steps. So this is a summary of those 4 steps. Interestingly, we did not, in the beginning, do this dictionary of entities, right? So the entities that we could anyway, we could have extracted was only things like people and countries and stakeholders and so on. But there was no way we could have extracted all the topics that were interesting, right? So, and also because the relations that we wanted were only of 2 kinds, like support and oppose, we started from simply, identifying snippets which were interesting to us. So, for example, this is a newspaper headline: Afghan president says he supports talks with Taliban, right? So that is a snippet which has an opinion, right? So candidate opinion snippets. And we had thousands and thousands of such snippets. Now, from each snippet, we had to do um, entity and facet extraction, because this part here he supports already gives you the relationship between a stakeholder here and a topic here, right? So support is the relation that we already know because the snippet already has it. But we need to extract the entity correctly, which is the Afghan president, and the facet or the topic, which is talks with Taliban, right? And we can do this for all the snippets that we have. And then comes the challenging part of coming up with canonical forms for these entities and topics. So at that time, Hamid Karzai was the Afghan president. So if we had extracted Karzai, then it had to be mapped to Hamid Karzai. If we had extracted Afghan president, then that also has to be mapped to Hamid Karzai. And Taliban talks with Taliban, they both map to Taliban negotiations. So that was the canonical form, right? And then once we had these facets, we wanted to organize them in a topic hierarchy. So Taliban negotiations was a topic, drone strikes, both of them come under Afghanistan war, and there is bombings, not bondings, suicide bombings, which come under the Iraq war, and both of them are part of the war on terror, right? So let me go into a few more details on exactly how we did these things. So the first step was to find candidate opinion snippets, right? So we basically looked at the web, and by the web, I mean the specific newspapers that we had decided on, right? And of course, Wikipedia itself was also a useful um, source. And the way we did it was to use these seed phrases as queries to the search system. So um, we had he supports. So he supports is a phrase that we fire as a query on Google. Similarly, she supports is another phrase we fire as a query. He voted for, he voted against, and so on. So there were some 10 to 20 different seed phrases that we came up with. And remember that we only wanted support and oppose, right? So it was easy to sort of think about how these phrases could occur in newspapers. So once we fire these queries, we get a bunch of results, and we gather those snippets. So here you can see several examples. A supporter of was a seed phrase query that we fired. Acknowledge that is another seed phrase. His support for is another seed phrase, right? So firing these phrases as queries gave us these three snippets. So with these snippets in hand, we need to identify the entity and the facets. And here is where it gets sort of very tricky to do, because we need to make use of parsers, right? Specifically dependency parser, because we have this a supporter of as our main phrase, and we want to find the subject and object of that phrase, right? And this is not a straightforward thing. And in fact, we needed to come up with lots of different heuristics to do this right. And in spite of that, there were a lot of errors, right? So in this first example here, it's fine because it has identified John Kyle as the entity and Arizona immigration law as the facet, and that is correct for this sentence. But this is a very simple sentence. Try the next one, right? Here, what the dependency parser identified as the entity was okay. Robert Gates is correct. But what it identified as a facet, not correct at all. And in fact, it's not even clear whether in this sentence you can identify a proper facet, right? It's quite tough. Even human beings looking at this sentence may not be able to come up with a proper topic to say that Robert Gates has supported this particular thing, right? So mistakes of this kind. And here is another example, which is again a mistake, right? So there are actually two people being referred to in this sentence: Prime Minister David Cameron and Mr. Gates. This was Robert Gates, who was the defense secretary of the US at the time. So two people have been mentioned in this sentence. The topic is correct, right? American strategy in Afghanistan, the topic is correct. But Mr. Gates is not the one who is supporting this in this sentence. It's actually David Cameron who's supporting this, right? So doing this extraction is, it requires a lot of looking at the kinds of sentences you have, coming up with a lot of heuristics to use, and it's a generally overall very painful process. Right. So once we had a reasonable set of entities and facets, we needed to come up with canonical forms for these entities and facets, right? So entities could include Gaddafi, Obama, and US president. And these raw facets are raw because they're simply phrases from the sentences from which we extracted them from, right? So you have UN mandate against Libya, use of force against Libyan civilians, military airstrikes, coalition airstrikes on Libya, and so on. So how do we go about canonicalizing these topics, right? So the first part of canonicalizing entity names was simpler, simply because we had Yago, which means that we had Wikipedia, right? So Wikipedia actually maps many different phrases to one particular entity. And you might have seen this, right? When you search in the Wikipedia search box and you type in Obama, then it actually asks you, did you mean Barack Obama? Did you mean Michelle Obama? Did you mean XYZ, right? So, in a sense, you have this relation sort of inbuilt in Wikipedia, that Barack Obama is typically referred to as Obama or President Obama or Barack Hussein Obama. All of them are the same person, Barack Obama. And in case there is the same phrase maps to two different uh, people, then just pick the one that is the most popular, which is what we did in this case. So most of the time it works, but obviously there are going to be some times where this is not precise, this is not correct. But again, this is something that we need to live with. So entities are good, but what about the topics or the facets, right? So this was another big challenge that we had. And again, we went back to Wikipedia, because Wikipedia is always, especially the title of the Wikipedia page, is always a good source for these labels, right? So by labels, I here mean just the canonical form. So it was a good source for these canonical forms, but the topic was not always controversial, right? So we cannot choose every Wikipedia title as a controversial topic. So instead, we made use of this other website called Debatepedia. You can actually check it out. It is something that is modeled just like Wikipedia, but there are a lot of debates on it. So there are lots of different political topics, controversial topics, and there is a pro and there is a con, pro and con debates, multiple debates that they publish on this Debatepedia. So since we were looking specifically for political and controversial topics, we first mapped our raw facets onto these Debatepedia titles. And then from Debatepedia, we could map to Wikipedia. And that is sort of how we came up with that. And finally, of course, we needed to organize things in a hierarchy. So again, this is something that different people would probably use many different kinds of techniques to do. So one possible way solution that we had was this. So all these nodes here are just the raw facets that we had extracted, right? So Iran's nuclear energy, Israeli nuclear energy, Iran's politics, bilateral relations of Israel, all of these are raw facets and we made a node for each of these facets. And then conceptually, it was a complete graph of these nodes. So every node connected to every other node, even though in this diagram it doesn't show the complete graph. Conceptually, it's a complete graph. And now we are going to weigh both the edges as well as the nodes, right? So what is the basis for this? Why are we doing this? So one is to sort of figure out whether this topic is interesting or not, right? So the criteria that we used here is that if there are a lot of facets which are mapped onto this topic, then this is interesting. And this edge weight basically tells us how close two particular topics actually are, right? So again, we looked at Wikipedia to determine this. So if two topics had, this is going to be one Wikipedia page, this is going to be another Wikipedia page. And if two topics
Excuse
have,
me,
yeah,
I have one query. How we are going to calculate these edge weights?
edge weights.
Yes, ma'am.
Yeah, that's what I'm saying here. I'm just talking about it.
Okay, ma'am.
So the way we are determining the edge weights, so what we want from the edge weights is to figure out whether these two topics, how closely these two topics are connected to each other, right? Because we want to construct this hierarchy, one of the things we want to know is how close these two topics are related. And this weight has to indicate how closely they're related, right? So maybe higher the weight, more closer they are. So again, you can come up with a lot of different ideas to figure this out. What we did was to look at how Wikipedia has organized these two topics. So there is a page in Wikipedia for this topic, and there is a page in Wikipedia for this topic. And both these pages have a lot of subtopics in them. And if there is a big overlap in the subtopics, right? So common subcategories, then depending on that, we assign a weight to this edge, right? And similarly, we do it for all pairs of nodes, and we can prune out nodes with no nothing in with no subcategories in common, right? So what we finally get is a weighted graph where the nodes are telling you how important the topic is, and edges are telling you how closely two topics are connected. Now, using this graph, we can do,
Ma'am, in this previous slide, actually,
yeah.
is it the case of, in the previous slide, yes, is it a case of word matching or something like that?
It's not word matching, it's from here, right? So the raw facets that we had, we mapped to Debatepedia. And again, the matching that we did was quite simple, right? So looking at things like Jacquard similarity.
Okay. Yes,
Okay.
similarity
So
matching.
lots of these raw facets from here, lots of these raw facets, we could map them to Debatepedia and Wikipedia titles. And they're going to be our topic canonical form, right? So once we have those, so all of these are now canonical forms for some set of raw facets. Okay, and now we want to construct a hierarchy based on these topics that we have. So we have constructed,
How this
yeah.
hierarchy maintaining, actually, creating. I mean to say, Israel-Palestine conflict is, I think it's a child of Israeli weapon of mass destruction.
Yeah,
Is it
so here
way?
is how we do it, right? So here is how we are doing. We are doing a clustering first.
Okay.
Okay, so we are doing a clustering first to say all these topics here are very similar to each other and they belong in one cluster. Same here and same here. Now we have the nodes of the hierarchy, but we want to know in which direction do we need to point. So is there an edge from this cluster to this cluster or from this cluster to this cluster? So again, that is something that is heuristic. Again, you can come up with different ideas as to how to do this hierarchy, right? What we did was to simply count the number of edges that go from nodes in this cluster to nodes in this cluster, and the number of edges that go from the nodes in this cluster to the nodes in this cluster. And whichever was higher, that is the direction in which we point the arrow. Okay, so as I said, this is just one of the ideas that we implemented, but I'm sure that there are a lot of, coming up with these canonical forms is itself a challenging problem to work on. And once you have that, coming up with these hierarchies and so on, there are lots of different kinds of ideas that you can come up with, right? Like this is just one method of doing it, but which seemed very interesting and nice because we got to do graph clustering and so on, but may or may not be the best way of doing it. So an interesting problem to work on, right? So just to summarize, I think I didn't mention the name of our opinion base. It's called opinionated. I actually don't know what this expands to, but it doesn't matter. And we did it in 4 steps like this. Okay. So I'm seeing that I've been quite slow and it's already 4 o'clock. Should we have a 5-minute break? Because I think what I might be able to cover is
Yeah, why
these two
not?
parts.
Yes, on your leave we can have 5 minutes break. There is no problem at all.
I'm sorry, Sarika, I didn't hear you.
Yeah, we can have a 5 minute break.
We can have a 5-minute break. Okay. So I'll see you guys back at 4:05.
Yes, please.
Okay. So it's 4:05. Should we start up?
Yeah, we can.
Yeah, I'll just share. Okay. So that was the opinion base. Let me now move on to something that's a little more challenging in different ways. A technical knowledge base, specifically for computer science, right? Okay. So,
Ma'am, ma'am, I have a query. Can I ask you?
yeah, yeah, go ahead.
Ma'am, what to do in case of disambiguating entities, ma'am? For example, if there
Ah,
is an entity called race, it belongs to ethnic groups and a sport. How can we disambiguate these entities uh, by
right.
linking them with Wikipedia or Debatepedia?
So, usually the way to disambiguate something is to look at the context in which that word occurs, word or entity, what is the context in which it occurs, and then you will be able to do it. So, for example, so this is just an idea off the top of my head, right? So, suppose in Wikipedia you do have both kinds of race, right? So, race as in a sports thing, and race as in which race does this person belong to, right? So, two Wikipedia pages. Now we can look at the terms that occur in each of these pages, right? So the what are the words that occur in the sports page and what are the words that occur in the race page, and now match it to the context in which you found found your word. Which of them is closer? So it's likely to be that.
Um, Okay, ma'am.
Did you get it?
Yes, ma'am. To match the similarity, what can be used as the better metric, ma'am? Is it Jaccard similarity or cosine similarity or some other better metrics, ma'am?
So actually, that is something that you have to try and see. There is just no hard and fast rule saying that some particular metric is going to work. Sometimes it works in certain circumstances and sometimes it doesn't. So it completely depends on what is the data that you're working with and what it looks like, right? You have to try multiple. So that's one of the problems in doing this work in language processing, right? So one size fits all never works. It's just that there are a bunch of different techniques and you just have to try each of these techniques and try to get a feel for what is the thing that is working really well for your particular application.
No, okay, ma'am.
Okay.
Thank you, ma'am. Thank you, ma'am.
Yeah. Okay.
Ma'am, can I ask one question?
Yeah, sure.
What is the meaning of context knowledge base? If I want to merge, suppose two knowledge bases, one is the suppose general knowledge base is there, and if I want to make that knowledge base as context, then how we can do that? Actually,
Mm,
I have made one ontology. Suppose that is a upper level ontology, and one other another ontology is there that is a context ontology. And if I want to make that general ontology or upper ontology as context also, then how we can do that?
hmm. Probably I'm not the right person to ask about ontologies. Mm, because I do not completely know the terminologies that relate to ontologies. So I'm not really sure what you mean by context ontology.
Okay, okay.
Um,
Actually, I was thinking like the ontology is just like a knowledge base. So, if I want to make that knowledge base as context, suppose, then how we can do that?
so
Or
I think we should differentiate between an ontology and a knowledge base because an ontology has rules for inference
okay,
and it has types, whereas a knowledge base, the raw knowledge bases that I'm talking about, they have none of it. There is no reasoning rules that are
Okay.
specified, nor are there types specified for the entities and the relationships. So adding an ontology on top of a knowledge base is, that is enhancing the knowledge base in a way, and saying, here are the specific types of these entities, here are the specific types of these relations, and so on, right? So I would say
Okay.
knowledge base and ontology are not the same. And the knowledge base specifically that we are talking about here do not have any ontology associated with them.
Okay. Okay, ma'am.
Okay,
Thank you. Yeah, thank you, ma'am.
right.
Ma'am,
Okay.
mm,
Any other questions?
yes, ma'am. When we are using ontology about the knowledge base, will it become knowledge graph?
Um, Not really. I mean, you just say it's a knowledge graph with ontology, right? Or this
Okay,
knowledge base or knowledge graph conforms to this particular ontology.
okay, ma'am.
That's how you use it.
Okay.
Also wanted to make you some statements regarding ontology, knowledge base, and knowledge graph. And you yourself has done in your last statement. A knowledge graph and a knowledge base should conform to an ontology.
Right.
Thank
No,
you.
if you have an ontology, then that's how you would relate the two.
Yeah, true.
You may not have an ontology because all the knowledge bases that I have been talking about, they do not have any ontology associated with them.
Do not have an ontology which they conform to.
Yeah, they could. I mean, we could make it so that there is an ontology associated with them, but the way I am talking about it, ontologies I have completely ignored from the picture.
Yeah, they are the knowledge stored. The triples are stored in a manner. The data, the facts are stored in this knowledge base.
Yeah. Okay.
Okay.
All right. So let me just move on to the next part. This is a knowledge base of computer science concepts. And I'm really proud of this name, Technobase, right? So again, the sources are crucial. So Wikipedia, the obvious source for anything that you want to do, we had Wikipedia with us, but also some very specific IT-related websites, Webopedia and TechTarget. You can actually check it out. They have different, they define different terms all related to IT, and they give an explanation for each terms. It's like a more elaborate dictionary for terms in information technology, right? And of course, there were lots of online textbooks that we made use of. Okay, I shouldn't say a lot of online textbooks, but there were a few textbooks that we could find online on various computer science topics that we thought could be helpful in constructing this knowledge base, right? And this time we actually started with extracting a set of entities, right? And the types of these entities are not known ahead of time. Like it's not like a person or a institution or a country. We don't know the types, except in a very vague sense. We know the types in the sense that they have to have something to do with computer science, right? So the types are not strictly known, but from Wikipedia, we were able to isolate all the pages corresponding to computer science and extract a bunch of entities from there. And we looked at indexes of these online textbooks because that's where a lot of technical terms are listed in those indexes. And we extracted a bunch of entities from there. This was so that we had quite a large dictionary of these entities. And the interesting thing that we did was extracting the relationships between these entities. And unlike for opinions, where we had exactly two kinds of relations and the sources were all unstructured, we made this relation extraction into four parts. So the first part is known relations. That is, we made the list of relations that we thought were interesting, and we had structured sources. So structured source in this case are Wikipedia, Webopedia, TechTarget. They're all structured sources because just even if you visually inspect these pages, you can see that they present their data in a very fixed format. So that's what I mean by structured. Maybe semi-structured would be a better term here, right? And the next thing we saw was known relations, but from unstructured sources. So this could be from the text of the Wikipedia page or the text of the Webopedia pages and so on. So the text is always unstructured source, but we know exactly what relation to extract from them. And of course, we won't know all the relations ahead of time, right? So there could be a lot of unknown relations, and we need to extract them from structured sources. And we have unknown relations, and we want to extract them from unstructured sources. So again, note the goal of this, because when we first started out, the goal was again very vague. It simply said map out the space of computer science concepts and how they're related to each other, right? It's a very vague kind of goal. And the applications that I listed before, they sort of came after it, even though they should have come, ideally before. That's usually not how research works. I mean, you start with something and then you expand on the idea and you find out that it's actually useful in this 5 different ways, right? So we started with this vague goal, which meant that we wanted every single CS concept out there, and we wanted every possible relationship among these CS concepts. We wanted to extract them. Okay, and the refinement part, I'm just going to not talk about it at the moment, right? So the first step, dictionary of entities, it was quite straightforward in the sense that these are all structured sources, right? They all present their data in a very fixed format, including online textbooks, right? Because we are only considering the indexes of these textbooks. So what we actually need is to write a smart program that will look at the page and extract the information out of it, right? So from Wikipedia, we looked at the category computing, and we had a whole bunch of pages from this computing category. And we were able to, and just looking at the titles of these pages, that's 54,000 entities that we were able to get from there. Similarly, Webopedia and TechTarget, 24,000 entities, and online textbooks, 16,500 entities, right? Of course, there are quite a lot of duplicates among them. And removing all these duplicates, we got about 70,000 entities at the end. So this was our dictionary, right? And then now that we have the set of entities with us, we now want to extract relationships among these entities, right? So here again, a lot of inspection of the data set that we had made a big difference. So just here, I'm considering one of the ways to extract relations, right? So from structured sources and known relations, right? So we made a list of these relations. So type of is a relation, subtopic of is a relation, application of, algorithm for, and technique in. So these are relations that we made a list of for ourselves, and decided that these relations can be extracted from these structured sources, right? And the snippets that I have here are directly from Wikipedia. In fact, if you go and look there now, you will find these structures, right? So there is a page called list of data structures. And it's not just list of data structures. There are lists of lots of different things, right? So we call them list of pages, right? List of pages. And here it says list of data structures, and there is a trees section there. Under that, there is a list with a list heading called binary trees, right? Under which you have lots of different kinds of trees listed, which are all binary trees. So just by inspection of this source, you see that it is structured in a very specific way. In fact, all the pages of this type, where it says list of something, are structured in this way. So we went to all those pages and we were able to extract relations like this. So here, binary search tree is a type of binary tree, right? So binary tree is the heading, and under that in a list, we have binary search tree. And binary tree is itself a type of tree, because binary tree occurs in the page of, under the heading of trees, right? And tree itself is a type of data structure, because trees occurs in this list of data structures page, right? So just using this sort of template, we were able to extract quite a lot of type of relationships. And similarly, the subtopic of, because here these are other sets of pages, list of pages, but which specifically say set theory topics, right? So whatever occurs here, you can be reasonably sure that there are topics that belong to this broader category of set theory, right? So we had Boolean valued model is a subtopic of set theory, right? Because it occurs in the page of set theory topics, Boolean valued model, subtopic of set theory. Similarly, algebra of sets is a subtopic of set theory, right? Again, application of, right? So if you look at this particular page on coding theory, and this is the contents part of it, which occurs in the very top of the page. There is one heading here which says other applications of coding theory, right? So the word applications occurs. So whenever it does, we extracted whatever is underneath it as an application of coding theory. So group testing is an application of coding theory. Analog coding is an application of coding theory. Similarly, for algorithm for and technique in, right? So you basically see it here in the heading itself. This is a page for document classification, and it says these are the techniques, right? So so naive Bayes classifier is a technique in document classification. Same with k-nearest neighbor algorithm. Same idea here. This is the page for derivative free optimization, and it here says in the heading that these are algorithms that it is listing underneath. So you say cuckoo search is an algorithm for derivative free optimization. MCS algorithm, the same thing, right? So simply by sort of visually inspecting the way in which the source is structured, right? So this is all from Wikipedia. So just looking at the pages and how they are structured, we were able to extract quite a lot of these relationships by simply writing these wrappers and using certain heuristics. Now, of course, it's always possible that we extract something incorrectly. In fact, the accuracy of these extractions is not 100%. It's just that I haven't shown you the mistakes that we have made. So don't assume that this was 100% accurate, because it was not. And we are not expecting it to be 100% accurate anyway, right? So just looking at this category of structured sources and known relations, we were able to extract these kinds of relations. Now, what about the other kinds, right? So structured source, but unknown relation, right? So the relation is not known to us ahead of time. And this actually occurred in one specific case where data is represented as a table here, right? So this is the databases page, the template databases page. And there are row headings here. And under these row headings, there are a lot of different concepts that are listed, right? So row headings sort of tell us the relationship between the topic being discussed, which in this case is databases, and the entities that are being listed in that particular row. So for example, data dictionary, which is here, is a component of databases, right? So component is the relation, object is a relation, and this could be potentially an entity, which is in this particular relationship with this particular entity, right? So again, in Wikipedia, there are lots of such tables, and in each table, these row headings are different from each other. So the relationship is not known to us beforehand, but it's again straightforward to write a wrapper which is going to extract these entities and relations. Again, it's not going to be 100% accurate, but we are willing to live with high precision but not perfect precision. So and then we look at this. Okay, so apologies for the spelling mistake there. This should be unstructured. Okay, I made a lot of errors. This is unknown. Okay, sorry about that. I'll fix that. So unstructured source and known relation. So again, looking at some part of the unstructured source, we were able to list out relations, so such as synonym of. So because in specifically in two of the sources, tech target and webopedia, we found that this synonym of relation is always expressed in one of these ways. So X is an abbreviation for Y, or it says BFS, and in brackets it tells you what exactly it is, right? Breadth first search, and X is short for Y. So we always found that in the text part of Webopedia and Tech Target, this particular relation synonym of could be easily extracted if we just did a search of these patterns. And we could extract relations like BFS, synonym of breadth first search, and regex, synonym of regular expression, and so on, using this. Okay. And finally, of course, there is the unstructured source and unknown relation. And I assume Sumit would have talked to you in the morning about open information extraction, right? So which just reads sentence after sentence and extracts relations and extracts the subject of the relation and the object of the relation. So for the text in our textbooks and Wikipedia, we actually ran OpenIE, right? And just running it raw gave us a lot of triples, like 400,000 triples. But most of them were useless. Starting from this first problem, which is that non-technical entities were in the result. So unfortunately, I don't have examples of these, but I think it's very easy for you to believe me. Or if you just run OpenIE, sometime on a piece of text, you will see how much of junk it actually throws up, right? So non-technical entities were there in the result. And this is where the dictionary that we had formed for entities came into picture, right? So we were able to just remove all those triples which had entities which were not in our dictionary already, right? This reduced the number of triples by almost 100,000. But the way in which we were able to match entities in the dictionary with the entities extracted by OpenIE was to use substring matching, because it is very unreasonable to expect that entities will occur exactly as they're present in the dictionary, right? That's very unrealistic to expect. There might be a hyphen more, or it might be in a plural form. All of these minor kind of changes could happen, but they're actually the same entity. So we cannot do a perfect string match when we are doing this matching. So we did a substring match, which eliminated quite a lot of triples, but we had these long phrases containing the entity name. So because the entity name was there as a substring and it was a good match for that, so we retained it, but they're not really good entities because they're too long. The phrases that contain these entities are too long. So we set up a reasonably high matching criterion. So unless there was a 50% match, don't retain them. And that just drastically reduced the number of triples again. At this time, the problem was generic entities. We had entities like the algorithm. So algorithm is indeed an interesting entity, but the algorithm is probably referring to a specific algorithm in the text, which OpenIE has not been able to recognize. So it simply says the algorithm is a kind of something else, right? So these generic entities were quite a lot in the set of triples that we had. And we could do one simple filter, which is to remove arguments or these entities which start with the. And suddenly there is a drastic decrease to just about 3,500 triples. And this was probably, we ran out of ideas about what other heuristic to apply. And the accuracy remained at around 65%. So we actually did an evaluation of how good these triples were, and this was all the accuracy that we had, right? And here are a few examples of things that we extracted. Again, the good ones, right? So I'm not showing you the bad ones that we got. So gigabit Ethernet. So the relationship itself is quite long, is a high-speed form of Ethernet. So Iron Python is an adaptation of Python. So these relations we would never think of on our own, right? So these relations come into play only when you do this sort of mm, unfiltered or unrestrained extractions. So I think I'm going to skip over the refinements again and move on to the next slide, which basically gives you some statistics. So this is sort of advertising the work that we did, the number of entities that we have, the number of unique relations, and the number of triples. And synonym of was the most common relation that we were able to extract. And this is just a summary of the statistics there. So I see now that I'm already at 4:30 and I should probably stop by now. Sarika, what do you think? I have about 3 slides, very small number of slides for this biochemical knowledge base. I can do that and stop, or I can stop right now and share the slides with you.
Those 3 slides. Please continue.
Pardon?
Please continue.
Okay, I'll continue then. Okay. So the last part, looking at the biochemical knowledge base, right? So first I want to point you to the goal. So unlike the previous 2 knowledge bases, we started this with a very specific goal because we wanted to answer questions of the form, is a specific microbe aerobic or anaerobic? Okay, this was the very specific question we wanted to answer. And the whole process of developing this knowledge base was so that we can do the reasoning. So I mentioned a little bit of it earlier when I showed you examples, right? So we can gather a lot of triples or information about microbes and reactions and so on. And then if an expert comes and says, here are the reasoning rules that you need to apply to figure out whether a specific microbe is aerobic or anaerobic, then we could make use of this knowledge base and the reasoning um, framework and answer these questions. Unfortunately, we were not able to complete the reasoning part of it, but we did succeed somewhat in constructing the knowledge base itself, right? So the sources, it was very clear that we need to look at research articles, so mainly unstructured sources, right? And the entities that were interesting were given to us by a few experts. So there was a list of entities that they said they're interesting, that are interesting to them, and they gave it to us. And they told us more such um, entities are interesting. So if they gave us, let's say, 25 microbes, they said microbes are interesting to us. So we could go out and look for web sources where microbes are listed and we could extract them as entities, right? And this last part is quite interesting because if the expert has already given us a list and we know exactly what type of entity to extract, why do we now need these pause tagging and heuristics, right? Why do we need to extract from unstructured sources? So I just have an example of that. I'll come to it in the next slide. And again, here, the relations were known to us. There were some 5 or 6 different relations that were interesting because, again, the experts told us that these are all the relations that you will need. And the sources were unstructured, which basically these research articles, that's where we needed to extract these relations from. And the main thing that we did, because it was unstructured sources and these relations were known, the method of choice is to train machine learning models to do this. Okay, so let me briefly go through the 2 steps. So acquiring the list of entities, we looked at quite a lot of different web sources. And I must say these web sources are very well organized and they're quite comprehensive, right? So we were able to extract lists of many different kinds of entities which are listed here, right? And here is a small excerpt from before, looking at the kinds of entities that we were interested in and the relationships, right? So the interesting part comes why we ever needed those part of speech tagging and so on. And that was because in the text that we see, rarely did we find these entities occurring all by themselves, right? So sediment might be an entity that the expert list has given us, or Antarctic or hydrocarbons. But along with sediments, you have this whole descriptive adjective with it. So it's not just a sediment, it's an aromatic hydrocarbon contaminated sediment, right? It's not just Antarctic, and it is hydrocarbon contaminated Antarctic. It's not just bacteria, it is aromatic hydrocarbon degrading bacteria. And there could be lots of other kinds of bacteria, there could be lots of other kinds of sediments, and so on. So we felt that, sort of getting this, depending on what kind of sediment or depending on what kind of bacteria, the properties would change, right? The reasoning would change. So the only way to acquire this was to again go for parsing and part of speech tagging. And that's what we did. So here were a bunch of rules that we formulated, right? So this E here corresponds to the entity that we were given, right? So hydrocarbon, Antarctic, biodegradation, sediments, they were all entities that we were given. And now we looked at the sentence and what the previous words were, right? So JJ is the tag for adjective. So if you use a part of speech tagger, it will tag this word aromatic as an adjective, and it will tag hydrocarbon contaminated as an adjective, right? So if there is an entity and before that there are a bunch of adjectives, then extract the whole thing as one single entity. Okay. Similarly, if there is an entity in the end, and this was a verb and this was a noun phrase, extract the entire thing as an entity, right? So we had these 6 different rules, again by inspection, right? So as you see the papers in front of you, you figure out, there are, the entities don't occur on their own. In fact, they have a certain set of properties associated with them, and you extract the entire thing as your entity. So we extracted quite a few entities of that kind. So once we had the entities, we next need to acquire the relationships among these entities. And the set of relations is known, and we need to extract them from unstructured sources. So here are the set of relations, right? So not only do we know the relations, the name of the relations, we also know the type of the relation. So what do I mean by type of the relation? I know exactly what should occur as the subject, what kind of entity should occur as a subject, and what kind of entity should occur as the object, right? So extracting found in relation means the subject of that relation has to be a microbe and the object of that relation has to be an environment. So an example is Pseudomonas is found in the sea. Yes, found in relation, subject is a microbe and the object is an environment. Similarly, the relation of is between a microbe and a property of the microbe, right? Acts on is between a microbe and a substrate. Carried on is between a microbe and a reaction or process, and so on. So we had this list of relations. We know the type of these relations, and we had a bunch of examples. So in these cases, unless you can come up with those substring rules, right? So unless you know how a found in relation is expressed in text, you need to go in for machine learning models, right? So this was our big pain point here, because we needed, in order to train any machine learning model, you need this gold standard data set. And we, being computer science people, we had to go look for biochemical people because they're the only ones who actually understand what's going on in those research papers, right? So, but we did manage to do it by recruiting students, a lot of students from the biochemical engineering department, create a gold standard data set for each of those relations. And then we trained lots of different models. Again, it's not like there is one particular model that works, right? Maybe for some things, linear regression works, or for something else, it might be SVM that works. So we have no idea which model works. So we have to try with a bunch of models. And then we have to evaluate the quality of the extractions for each of the relations. Because one relation might have very high accuracy in a particular model, but another relation might have a very low accuracy in the same model, right? So it is perfectly possible that for each relation, we need to train different models, right? So this is really an iterative process, starting from whether to use the same features or more features, different features, whether to acquire more training data, whether to train different models, how your tuning should go. So this, we had to do quite a lot of iterations before we can actually extract the relations there.
Ma'am, hello, ma'am.
Yeah, go
In
ahead.
case of machine learning, each relation that you are talking about, what is the model will give as an expected output?
It will say whether or not this particular sentence contains this particular relation.
Is it present or absent like this way?
Yeah, exactly. Or you give a phrase to it and it says whether this corresponds to this particular relation or not. Right? It's basically a classifier.
Okay, classifier.
Yeah.
Okay.
Okay.
Okay, ma'am.
All right. So I think I'll stop here because there is no time for part 2 of the talk. So I hope
I can see a lot of queries in the chat box. May I?
Sure, I can answer the. Do you want me to answer in the text box itself? I can do that for a while. Otherwise, I can.
This is possible, and the participants can ask the questions if they want. Otherwise, you can read the chat box.
I'm sorry, I can't hear.
Okay.
Let me just read it myself. Right.
Sarika ma'am, your voice is not audible.
I'm not audible at all.
It's very faint.
Okay. So let us compromise. Let us look it for 5 more minutes. Please read the queries.
Yeah, I can do that myself. I can read the question and I can answer it.
Yeah.
Okay, so let me.
Start
Okay. Start from.
Ma'am, can you please show the future directions slide, ma'am?
I actually did not make it a researchy kind of talk. So I think there is a lot of work to be done just in domain-specific knowledge bases, right? So just try building one of these knowledge bases with some sort of application in mind, and you will see that there are a lot of problems which are completely unsolved, and you won't even find papers which attempt to solve them, right? So I think one way to get into this area is to have some sort of industry collaboration. These industry guys, especially for that biochemical KB, that problem came about only because of these guys from ExxonMobil, who said we want to solve this problem. We want to find. So I guess I didn't tell you why that goal of answering the question is the microbe aerobic or anaerobic, right? So this question ExxonMobil wanted answered because they said that the presence of certain kinds of microbes in certain kinds of environments indicates whether there is oil there or not, right? So their goal was to search for this oil, and they wanted to make use of the large amount of research that has been done in order to figure out where they should look. So where they should look for places where certain kinds of microbes occur, right? So they wanted a computational way of getting this out, and we proposed this solution that we would organize the data in these research papers in this format as a knowledge base, and then you give us the reasoning rules, uh, which we can make use of and try to come up with the answers to your question. So similar to this, I'm sure there are lots of people out there who would benefit from organizing the data in this way. So I would say that is finding these interesting application areas is a research all by itself.
Okay, ma'am. Thanks.
Abhishek,
Okay.
Abhishek,
Yes, ma'am.
please ask your query.
Okay, ma'am. I wanted to ask first. I wanted to just get it clear. Like Wikipedia, is Wikidata and Yago also support different versions in different languages?
Yeah. Yago, I know that that team actually has a multilingual Yago. You
Okay.
just have to go to their website. I think you will get the details there. Um, in fact, one of my colleagues, he worked on this multilingual version of Yago, looking at different versions of Wikipedia, like in different languages, and extracting from them. In fact, even Yago, I think the source code is made available right now, so you can definitely try it out.
Someone, what's
So
the
the
name? What is
person
the
who
name?
worked on this multilingual Yago is Gerard Dumello. So you can look at his webpage and see what he's doing uh, these days, right?
Okay. So, ma'am, my second part was if they are available in multiple languages, then like combinations you talked about, like known relation and structured sources and unstructured sources. So, how can we approach if we are working with multiple languages?
Deal with each language separately, and then try to see how to link one language with the other. That could
Uh,
be one way of doing it,
okay.
right? Basically, what you need is to say this part which is expressed in language X, is it the same as this part expressed in language Y, right? So the entity which is expressed in language X is the same entity in language Y. Or the
Okay.
relation in language X, is it the same as the relation in language Y? And that can be a sort of post-processing step that you can do. But I really recommend that you look at this Gerard Demello's work. He did work on this multilingual Yago, and I think he identified quite a lot of interesting issues, and he solved them um, pretty well. For his PhD, he worked on this, so there should even be a thesis that you can start with.
Okay. Okay.
Okay.
Archana, you have a query? Sonika, madam?
Yes, ma'am. Yes, ma'am. How the information extraction is done for knowledge bases? As we are talking about right now, we are talking about relation extraction. So, how the information extraction is done for knowledge bases?
So I think I highlighted a bunch of different methods, right? Um, Relation extraction is basically information extraction.
Okay.
Any other participant wants to ask something from Dr. Maya?
I can answer these questions offline if you like. Um,
Yeah,
Maybe
definitely.
send you a document or something which you can put up,
Yeah, this is
because I have this chat window with me.
yeah. We are even preparing a fact if there are some questions later on also, we'll pose them to you.
I'm sorry, I just couldn't hear what you said. Your voice is very faint.
Okay, I don't know why. I think we are done otherwise. If the participants are not asking anything now, we are done.
Okay, I think I went way over time anyway, so thanks for not falling asleep, I think, after the lunch.
That is perfect.
um, I'll get back to you guys with some responses to the questions that you have here later on today or tomorrow.
Yeah.
Okay.
Thanks, ma'am.
All right. Thanks a lot.
Maya.
Thanks a lot, ma'am.
Bye.
Okay.